All right, hi everybody, this is Mr. Zarzak, and I'm going to take you through a quick calculation using Newton's law of universal gravitation. Okay, so Newton's law of universal gravitation is this formula, g m1 m2 over d squared, where g is this constant, this 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay, so in class, all right, you're probably going to be at some point asked to calculate the gravitational force between you and the person next to you. Okay, so in order to do that, okay, we're going to take and we're going to do two hypothetical masses. All right, most people don't know their mass in kilograms, but they know their weight. So let's say person one here is 100 pounds. Okay, so we're going to take that 100 pounds, okay, and to convert that into kilograms, your conversion factor is 0.45 kilograms for every 1 pound. Okay, which means that someone who's 100 pounds is 45 kilograms. Okay, so we'll make that person one. All right, person two, we'll make them 200 pounds. All right, so convert that. It's 0.45 kilograms per every 1 pound. Okay, so M2 here would be 90 kilograms. Okay, once you got those values, okay, I'm just going to make them a little bit smaller, just kind of tuck them away here. So 45 and 90. All right, so then to use Newton's law of universal gravitation, that's the equation g m1 m2 over d squared. Okay, so I'm just plugging into this equation. All right, so that g, that's that number from up here, so that's at that 6.67 times 10 to the negative 11th, these weird units, Newton meters squared per kilogram squared. Okay, those are just there because they make the equation work. I'm going to take that, I'm going to multiply by my first mass, which over here that was 45 kilograms, and then my second mass, which is 90. Okay, so I just go times 45. Okay, and then I go times 90. All right, I'm going to take all of that and divide by the distance between them squared. So we're going to put our people 1 meter apart just to make this really simple. Okay, so first time we're doing this calculation. All right, so this is what I'm going to go to do in my calculator. Now, when I do my calculation, I'll show you on mine, but just so you can see this, I took a screenshot of my calculator, okay, just so you can see it. The best button, in my opinion, on the calculator, okay, is this button right here, this little EE that stands for Engineering Exponent. Okay, so I'm going to reference that quite a bit. If I say I'm going to hit the EE button, that's the one. Okay, also, when I'm dealing with exponents, all right, I need to make sure that I'm using this. This is make it a negative number, okay? Don't use this. That's subtract, okay? So this is the one that we want to use in our calculator. All right, so anyway, so going back to this, I'm going to plug this into my calculator. All right, so let me bring my calculator up. All right, so here it is. Turn it on here. All right, oop. Okay, so if I want to type this 6.67 times 10, okay, and then I'd have to hit that little caret that's above the division sign, minus sign 11, okay, so 6.67 times 10 to the negative 11. If you notice, it says over on the right 6.67 e negative 11, okay, so that's like a shortcut. All right, so I can actually use that shortcut. I can save on how many keystrokes I have to type on my calculator, and I can avoid having to use parentheses, all right, by using this EE button that I just told you about. So I press the second key, which on my calculator is blue, it just turned red, okay, and then right above the 7 is that EE sign, so I'm going to hit that, okay, and then I'm going to hit the little negative sign, okay, that's down on the bottom, not the subtraction, okay, the negative sign, negative 11. Okay, and notice I've got the exact same value. Those two numbers are equivalent. Okay, so then I could just take, and with no parentheses required, multiply by my first mass, which was 45, multiply by my second mass, which was 90. Okay, so I've got g m1, m2. Okay, I'm going to take and divide that by the distance, which was 1 squared. Okay, so that's the way that I type it in, and my calculator is going to say 2.70135 e to the negative 7th, 2.7 e to the negative 7th. All right, so let me jump back over to my notes. All right, and so what this is the force of gravity, the weight here, okay, is this 2.7 e to the negative 7. Okay, my units are Newton. That's what we call engineering notation. We could write this in scientific notation, 2.7 times 10 to the negative 7 newtons, okay? Or I could write this in what's called standard notation, which is like normal numbers, I guess, which would be 1, 2, 3, 4, 5, 6 zeros, and then 2, 7. This is the same as 2.7 e to the negative 7, or 2.7 times 10 to the negative 7. Okay, all of these numbers here are the exact same number. Okay, why the different notations? Okay, we use scientific notation when we're interested in keeping track of sig figs. Okay, we use engineering notation when we're trying to do quick calculations with numbers that are really big or really small. Okay, we're all taught standard notation to begin with. Okay, when we're dealing with numbers that are really big or really small, all right, it's real easy to make a mistake having to write all these zeros, and it's kind of a pain to have to write all these zeros all the time. So we've invented a different way to represent numbers that allow us to not have to do that. Okay, so all three of these numbers are the same notation. All right, I'll do one more here real quick. Okay, it says how strongly you're attracted to Earth. All right, so I'm just going to, again, I'm going to use this sample mass, okay, of 90 kilograms. So this would be for a 200-pound person. Okay, if you want to use a different number, go ahead. It doesn't matter. All right, so I'm going to go G, M1, M2, divided by D squared. Okay, so now if I'm going to do this for how strong I'm attracted to Earth, okay, well, when I sub in my numbers, okay, the G, that big G, that's the universal gravitational constant. So I'm going to write that as 6.67. Okay, I'm going to do that in engineering notation to make this, just so you get familiar with it. E to the negative 11th, okay, Newton meter squared per kilogram squared. Okay, so now one of my masses is going to be this 90 over here. Okay, for the other mass, okay, well, Earth pulls on us. We pull back too, but if we're going to use this, okay, for the attraction to Earth, we've got to use Earth's mass. Okay, so there's Earth's mass. So 5.9742. Here, I'm going to use that E notation too. E to the 24th. That's times 10 to the 24th kilograms. All right, and then the distance, okay, so when we do the distance, so like if that's Earth, okay, if we're up here on the Earth, the distance that we care about is the distance down to the center, okay? That's the radius of the planet, okay? So I looked that up, the distance to Earth's center. It's that number right there. That's 6371000 meters, so 6371000 meters, and I have to take that number and I have to square it. Okay, so this is what I'm going to put into my calculator. All right, so let's all do that together real quick. All right, so again, I'm just going to start with that 6.67. Okay, I'm going to hit the second key. I'm going to hit that EE button right above the 7. Okay, minus sign, not the subtraction, the minus sign, negative 11th. Okay, times my sample mass of 90 kilograms, times the mass of the Earth, 5.9742. Second key, EE button above the 7. 24th, 5.9742 times 10 to the 24th kilograms. Okay, divided by that distance that was 6371000 squared. Okay, and this number, 8.3553, blah, 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 e to the 2. Okay, so here, let's take that number. One more time, 8.835. Let's do, I'll give myself a little bit of space. Okay. 8.335 e to the 2. Okay, that's the same as 833.5 newtons. That would be standard notation. I guess I could write it in scientific notation too if I wanted to. That'd be 8.335 times 10 to the 2 newtons. Okay, honestly with this, it's just easier to write it like that. Okay, but that's it. That's your weight, okay, from the Earth. All right, if I wanted to compare that, okay, all I would need to do is take my mass, that 90 kilograms, and multiply that by 9.8. 90 kilograms, 9.8 meters per second squared. Okay, if I throw that in my calculator, let's go ahead and do that real quick. So, oops, 90 times 9.8, I get 882. So this 882 newtons, okay, we say that this is equivalent. Okay, the little 1.5 Newton difference is honestly because this mass of the Earth is rounded. Okay, I know it sounds crazy, but this is 2 times 10 to the 20th power, okay, which is like the mass of the moon. It's ridiculous. Okay, so that's where our imprecision is. So because we rounded the mass of the Earth, we get a difference of like 1.5 newtons. But 1.5 newtons is less than 1%. Okay, close enough where we can call these equivalent. Okay, so there's some basics with using Newton's law of universal gravitation. This is Mr. Zardes saying thanks for watching, and I'll see you around west.